Welcome to our exploration of K nearest neighbors, or KNN, one of the most intuitive yet powerful machine learning algorithms. KNN is a supervised learning algorithm used for both classification and regression tasks. Its fundamental principle is remarkably simple. It makes predictions based on the similarity to known examples. KMN is unique in being both instance-based and lazy. Unlike eager learners that build models, during training, KNN stores all training examples and decision-making until prediction time. This approach gives it remarkable flexibility but comes with its own trade-offs. Let's understand KNN through a practical example. Here we're classifying fish species based on their length and lightness. The red dots represent salmon, blue dots are sea bass, and green dots are trout. When we encounter a new fish, shown here in yellow, KNN identifies 5 nearest neighbors. Notice how the algorithm determines the fish's species based on the majority class among these neighbors. The choice of K is crucial in KNN. With small k values, like 1 to 5, the model becomes highly sensitive to local patterns, but risks overfitting. Larger k values create smoother decision boundaries, but might miss important local patterns. A common starting point is to use the square root of your sample size, though cross-validation helps find the optimal value. KNN relies heavily on distance metrics. For continuous variables, we commonly use Euclidean distance, shown here in yellow, or Manhattan distance, shown in green. The choice depends on your data's characteristics. Euclidean distance measures straight line distance, while Manhattan distance follows grid-like paths. For categorical data, we use Hamming distance, which simply counts the number of mismatches between attributes. In our example comparing two strings, the Hamming distance is 2 because they differ in 2 positions. Normalization is crucial for KNN. Look at this example with age and income data. Without normalization, the income feature completely dominates the distance calculations due to its larger scale. After normalizing to a 0 to 1 scale, both features contribute more equally to the distance measure. Let's explore 3 key normalization methods. Min-max scaling transforms features to a 0 to 1 range, while z-score standardization centers data around 0 with unit variance. Feature scaling maintains relative relationships by dividing by the maximum absolute value. KNN's strengths lie in its simplicity and flexibility. It handles multiple classes naturally, requires no training phase, and makes minimal assumptions about data distribution. With larger k values, it becomes quite robust to noise in the training data. However, KNN faces several challenges. As dimensionality increases, data becomes sparse, making distance measures less meaningful. The algorithm requires significant memory to store training data and can be computationally expensive during prediction. Choosing the right k value and handling irrelevant features remain ongoing challenges. In real applications, we must consider feature importance. Not all attributes contribute equally to predictions. Instance weighting helps prioritize more relevant examples. Missing values require careful handling through imputation or interpolation techniques. KNN excels in various domains. In medical diagnosis, it has classified diseases using patient metrics, with recent cases weighted more heavily. Credit risk assessment relies on financial features, particularly payment history. Facial recognition systems use KNN with carefully selected facial landmarks. To implement KNN effectively, remember these key components: proper feature normalization, appropriate distance metric selection, and optimal k-value determination. While conceptually simple, successful implementation requires careful consideration of data preprocessing, feature importance, and computational efficiency. Understanding these fundamentals will help you apply KNN successfully in practice.